The last couple of classes, we've looked at filtering of digital data. In this class, I want to turn to interpolation of digital data. So in the last couple of classes, we were kind of solving a problem of how do we filter an interesting signal from maybe noise or maybe other signals. In this class, we're kind of addressing the problem of how do we interpolate data points to the regions between the data points. Over today's class and the next class, we'll look at two ways of doing that. One uses what's called a Lagrange polynomials, Lagrange interpolation, and the other one uses sort of a spline method in which we use piecewise polynomials for the interpolation. Anyway, today we'll work on the Lagrange interpolation, and on Monday we'll work on the spline interpolation. So the point here, or the importance here, the purpose here, is that many modern sensors or detectors or instruments give us or generate a discrete array of data points. So they might give us a discrete array of temperatures versus times in discrete time intervals and discrete temperature intervals. Or they might give us a discrete array of voltages versus time in discrete times and discrete voltages. But physical laws, physical understanding involves kind of continuous functions and involves laws involving differentiation of continuous functions and integration of continuous functions. So we're interested in the continuous function beneath, kind of underneath these discrete data. And so interpolation is a method of interpolation approach to interpolating to find the function, the smooth function, beneath the discrete data, the digitized data. Specifically, we're going to find some function, I'm going to call it f of x, that underlines some measured data points, xi, yi. I've indicated it here. So if we want to picture this situation, think of this plot over here on the right-hand side. So x is a independent variable horizontally. Y is the dependent variable vertically. We've got some sensor or detector or instrument. It's measured. It's determined a series of discrete data points. So here's x subscript 0, y subscript 0, x subscript 1, y subscript 1, and so on and so forth, the red data points. And we want to find the this smooth function, I called it f of x, I indicated it as blue, that kind of underlies those data points. So we want to be able to interpolate the value of the function between the measured data points. So that's the problem we're going to solve. And we're going to solve it in two different ways, one in today's class, one in the next class. There's kind of a special case of this interpolation, and that's when you have equally spaced data points. So there are special methods for equally spaced data points. And then there's the general case where you have, in general, unequally spaced data points. So, and we'll work on Lagrange and spline methods. We'll work on both equally and unequally spaced data points. So to begin talking about Lagrange interpolation, I want to first talk about the interpolation theorem. So it's a mathematical theorem. We're not going to prove the theorem, but it's a provable theorem related to a polynomial that can be matched to a set of discrete data. So if you look at this overhead here, what I'm imagining is I've got a set of data, this set of independent and dependent variables, xi, yi. And I've plotted again this example of data points here. For this particular interpolation theorem, we're going to consider that there are no repeated values of the independent variables. So none of the xi's have the same value. Therefore, none of the yi's have the same value. They're all different points of xi's and yi's. Then the interpolation theorem says that basically, if there's a unique polynomial that you can pass through the set of data points, supposing you have n data points, there's a unique polynomial that passes through those data points that has a degree of n, the number of data points, or less. So if you had 2 data points, for example, obvious case, right? There would be a unique polynomial that you could pass through those 2 data points that has an order of 2 or less. So it could be a linear polynomial, a linear term and a constant term. It had 2 terms. So in general, that makes sense, right? If you've got 2 data points, you can draw a straight line through those 2 data points. If you had 3 data points, then the interpolation theorem says that there's a unique polynomial, which would be say a quadratic in general, that would pass through those 3 data points. So you know that if you've got 3 data points, you can put a quadratic curve through those 3 data points. And then it's just that the interpolation theorem is just a kind of generalization of that. If you have 4 data points, you can always put a unique cubic function through those 4 data points. If you had 5 data points, then you'd have a corresponding polynomial that would go through those data points. So the interpolation theorem means that whatever way you find the kind of the lowest order polynomial that goes through your data points, whatever way you find that lowest order polynomial is the correct polynomial that goes through those data points. And we'll look at several methods for finding the polynomial that will pass through the data points. So on this slide, and the next slide, and the next slide, I just got 3 ways of solving the problem of finding this polynomial, the interpolating polynomial that goes through your data points. And so this way uses linear algebra. The next way uses a set of polynomials called Lagrange polynomials. And then the third way is using a library function, a SciPy library function. So I just wanted to walk through those 3 ways. You know, in practice, you probably use the SciPy function, but these 2 other methods will give you a kind of understanding of how that function works, how to determine these interpolating polynomials. Okay, so if we just walk through this argument here, right? And we imagine this data over here on the right-hand side. I've got in this data endpoints, say. In this particular case, I've got six data points, and I want to find a polynomial that has this form that exactly goes through these data points here. So if I've got these 7 data points here with labels 0, subscript 0 to subscript 7. And I want this order polynomial here, where this would be x to the n, 7 in this case, 6 in this case. And each one of these terms would have a coefficient determining the size of that contribution of that particular power of x to the polynomial. So we want to find this polynomial. So one way you can find this polynomial is if you write this this relation here, this polynomial here, out for each of the data points. So the way I've written the polynomial here is like x is a continuous variable, and p of x is the function that's passing through the data points. But I could write this equation out for each of the data points in my plot over here on the right-hand side. So in this particular case, because I've got 7 data points, I could write this equation out 7 times with, say, in the first equation, this would be kind of y0, the value of the polynomial for the 0th point, and the x's would be the x zeros. And then I'd have a corresponding equation where this would be y1, this data point here, and the x's would be the x1s. And so we'd have 7 of those equations. Those 7 equations you can write more compactly in terms of a sort of matrix vector equation, which is what I've written down here. So that set of 7 linear equations you can write out like this. So this matrix here is a matrix that contains in the columns the various powers of x from x to the n. So in this case, it'd be x to the power 6 through to x to the 0 in this column on the right. This vector here are the coefficients. So there's 7 coefficients for our data here that define the 7 terms in the polynomial. And then on the right of the equal sign here, this is the array of dependent variables in the discrete data from y0 through to y to the 6 in this case here. So you can imagine if you took this vector A here, this column vector A, and you multiply this top row by that vector A, then that's going to give you y0. So that represents this data point here. If you take this vector, column vector A, you multiply the second row in this matrix, then that will give you the value, the y value of this point here. So that'll give you y1, and so on and so forth. So it's just writing the 7 linear equations for the relationships between the 7 measured data points in matrix vector format. Okay, so this is the form of the relationship that we've constructed. M is the matrix. A is the column vector of the coefficients in the polynomial, and Y is the column vector of the dependent variables, and we want to find the A's. So the A's define the polynomial that goes through these data points, and so we want to solve this linear equation for A, and you can solve this linear equation for A by just multiplying through on the left-hand side and the right-hand side by the inverse of the matrix. So if you multiply by the inverse of the matrix M, we're going to get the unit matrix on the left-hand side, and we're going to get M times the matrix, the inverse matrix times Y on the right-hand side, and that'll be the solution for A. And so this is one way of finding the solution for the coefficients, is to calculate this product of the inverse matrix and the vector Y. So we'll go ahead and do that and see an application of that. This matrix comes up in interpolations, and it's called a van der Waals matrix. But basically what it does is if you've got that matrix, it allows you to, it basically allows you to map, that matrix plays the roles of mapping the coefficients of the polynomial onto the values of the polynomial. So if you think about how it's operating here, here's the coefficients of the polynomial, multiplied by this, it maps it onto the values of the polynomial. And that's a van der Waals matrix. So that's one way of solving the problem. So here's a second way of solving the problem that involves a set of polynomials that are called Lagrange polynomials or Lagrange basis polynomials that again crop up in this problem of interpolation. So again, we want to find the polynomial. So here's the polynomial, it's a function of x that describes the data points. The measure goes through the measured data points. And so that polynomial, the Lagrange solution to that polynomial is given by this little expression here, where this on the left-hand side is the polynomial, on the right-hand side is a sum over the n plus 1 data points. So in our case, we've got a sum over 7 data points, where what we're summing is the product of each dependent variable, so that's the yi's, times this quantity here is called ci, and it's a set of coefficients that are weighting the dependent variables that are constructed from what's called Lagrange polynomials. And so this again, I'm not proving this expression here, but this is a way of constructing that polynomial that goes through the data points. You're constructing that polynomial that goes through the data points by computing it from this sum of this product of your data points with these Lagrange polynomials. And downstairs here, I've written out the Lagrange polynomials. So the Lagrange polynomials are functions of the independent variables, so x, and they involve the measured values of the independent variable. And so this is the expression for the Lagrange basis polynomials that you plug in up here and multiply your dependent variables with. So if you look at this expression, firstly, it's a sum of it's a product of a bunch of terms that look like this, where there's a term again for each item of data that you have. So this product runs from 0 to n, your number of data points. And it's a product of pieces that look like this, where here's an important point. This x here in the top left, that's a variable. That's the independent variable. Whereas the x's with the subscripts, the xi and the xm, they are the values of your data points. They're the x values of the data points. So they'll be entered as numbers, whereas x is a variable, and it corresponds to these ci's being Lagrange polynomials that are functions of x. Here I kind of written it out in full what that product is. The xi, it corresponds to this particular the particular polynomial. So these polynomials, if we've got 7 data points, we're going to need 7 of these polynomials from C0 through to C6. And the xi matches the particular polynomial that we're calculating. And then the xm, that's the one that we're summing over. So that's the one that there are, in our case here, are 7 data points. There would be 7 terms, but you actually don't include the term where M is equal to I. So if you have 7 data points, in each product, there'd be 6 terms. If you had 2 data points in each product, there would be just 1 term. You have 3 data points in each product, there'd be 2 terms, is what this summation is saying. Okay, so that's a second way of calculating the polynomial, right? You're going to calculate the polynomial by calculating this sum of this products where the yi is your data points and the ci's are these Lagrange basis polynomials, which are also dependent on the independent variables in your data. And then the third way we're going to look at calculating the interpolating polynomial that goes exactly through the data is using a library function. So SciPy has that package has in it a interpolation library. There's various ways of interpolating. We're looking at one of them. And there's a function, Lagrange, that will do the interpolation for us. So in that function, you pass the arguments of your arrays of dependent and independent variables, and it's actually going to return to us a polynomial that represents the interpolating function. I'll say more about the polynomial when we get to that point. So this is the third way that we will solve the problem.